AI can often produce steps, but hard mathematics uh, is not steps. It involves something much deeper than that. Okay, hard mathematics is something that is a control over assumptions, right? That's the way to phrase it. Hard mathematics is control over your assumptions. Okay, there is no room for uh, assumptions. Well, there is, but us mathematicians define things in a very precise and logical way. Okay. In this video, I'm going to discuss some thought-provoking questions as usual. Okay. Number one, what is the difference between showing an example and proving a statement? Okay, that's question one. Question two is, why do quantifiers change the meaning of a calculus claim, statement, or proof? Okay, so that's very important. That's question two. Question three is, why is a counterexample sometimes even more important than just doing regular calculation, right? Why is it more important? Okay. Number four, okay, what does it mean to verify a theorem's hypothesis? Okay. And then question number five, why do students lose marks even when their algebra looks correct? Okay. So let's get right to the point, right? Let's get right to the meat of this video. Okay. As usual, STEM Online Academy is a no-nonsense mathematics and physics academy for university-minded students. All right, I'm going to show you right here. Okay, I'm going to play a simulation of what we're going to discuss, and hopefully can partially answer the questions I just brought up. Okay, but I'll be putting it in my own words and my own logical framework. All right, so question one, what is the difference between showing an example, right? Between showing an example and proving a statement. Okay, an example is just to give some sort of a I wouldn't say framework precisely, but what I want to say is that it gives us something to intuitively help the viewer or student, whoever is reading, who's ever reading our statement, deeper into us and deeper understanding to the problem, if that makes sense. Okay, you always want to be able, you always want to be able to, uh, in your proofs, uh, not always, it's not always necessary, but it really helps bring context, if that makes sense. Uh, Context to what we want to get our logic across, if that makes sense, right? That's the importance of what a mathematical example is. Okay. The difference between that and proving a statement is when you prove a statement, the example is not good enough. You need to show a rigorous, defining, airtight, step-by-step process uh, of all assumptions. Okay, there can't be just assumptions and examples, right, for a proof. So that's the difference between the proof and example. The proof tells us exactly um, how we want to show that the problem. Sorry, the proof shows us exactly um, everything that we need, everything that needs to be shown in a logical step, logical rigorous step, in an airtight way. Okay, right? There's no room for any slight assumptions or anything else in that sense. No ambiguities are allowed whatsoever. It has to be 100% airtight. Whereas the example, it helps us get our point across for that proof, but it's not a proof. Okay, so that's cool. That answers question one. Okay, by the way, I hope you're also paying attention to my simulation that I've drawn up. Okay, it's very relevant to the way I am answering these questions. Question 2, why do quantifiers change the meaning of a calculus claim? Okay, why do they change the meaning? Right? Or more specifically, why do quantifiers, not just any quantifiers, why do the commutative um, statements change the meaning of a calculus claim, right? Well, there's a very big difference for saying for all x in I, as you see right there, right? For all x in I, for all x in an interval I, right? Here's an example, right? So for all x in the interval I, as opposed to there exists an x in the interval I. When I say for all x in I, I'm actually, the implication of that statement is saying that uh, it's ranging across all x in the interval. Okay, right? So all x in the interval, right? So in that interval, there's a multitude of x's, right? We have different x values ranging within that interval. So that's what we mean by for all x in I, right? Now, here's another example. If I said there exists an x in I, it's a very different statement. Okay, that means that there is some x in I, right? Or specifically, there's one specific x in that interval that satisfies f prime of x equals 0. There pops up again. This is just an example to get my point across, as I mentioned in question 1, right? The example to get my point is to get the person's point across. Okay. So that's an example of why quantifiers change the meaning of a calculus claim, right? All right, question 3. Let's answer question 3. Why is a counterexample sometimes more powerful than computation? What do you think about that? Why is a counterexample much more important than computation? Well, because the counterexample, right, is all you need is one counterexample to either prove or disprove a claim. Okay, all you need is to find one counterexample, and you can automatically disprove a logical argument, or what is perceived as a logical argument. Okay, whereas a computation, right? A computation does not give us a rigorous. It's not enough evidence, or not enough rigor, to justify, right? To justify that someone's claim is either correct or incorrect, right? Or to disprove a claim, right? So I hope you understand the depth of what I'm saying here between a counterexample and a computation. The computation is just going to tell us, I mean, it indicates that something is wrong, right? In a proof, right? If you want to disprove an argument, for instance, right? Okay. Whereas a counterexample, if you find one counterexample and shown with rigor, you automatically disprove the argument. Okay, so there's a difference between those, and why a counterexample is much more powerful. Does that make sense? So I hope you're taking some very important lessons from this. Okay. Question 4: what does it mean to verify a theorem's hypothesis? I want you to think about that. What does it mean to verify a theorem's hypothesis in reality? Think about it. What does it really mean? Well, what it means is that you are verifying, or you have an approach to a conjecture. If you're verifying the conjecture, in reality, you're actually proving, right? You're proving mathematically what one's guess was. Okay, so when we say we want to verify a theorem's hypothesis, we're pretty much saying verifying a theorem's conjecture, to be more precise, because in mathematics hypothesis is a conjecture, and that conjecture tells us quite often um, what we may suspect this theorem is telling us, right? We have a hunch what it is, but we can't quite prove it. We don't have proof, right? So if we're able to prove it, we're able to verify that our suspicion or hunch is 100% correct. But we have to prove the conjecture. Otherwise, it's just something that is just that we have um, suspicions. We're, we're speculating what it is, but speculation is not enough in mathematics. Okay. And then finally, question 5. Well, before I get to question 5, I want to relate to you guys, my audience, okay, with one very important thing. Okay. When I was, and it's probably relevant to this video, when I was in junior high school to early high school, there was a point in my math journey where I was a disaster. Okay, I was having so much trouble with mathematics, not because I couldn't learn mathematics. I was learning the wrong things. Okay, I was learning how to algorithmically approach mathematics, and that's not what you want. Right? Unfortunately, our schools are doing too much of that. I'll give you an example. Solve um, solve the quadratic equation x squared plus 2x plus 1. This is your homework. Next question, solve x plus 3 squared. Next question. So you get the idea. They say, and the teachers are assigning homework that they say is going to prepare students. In reality, it's not preparing students for success, it's preparing them for failure. Okay? And that's a major problem. And I experienced this very early. Thank God I met 2 teachers that woke me up to uh, the education system's a trap to make sure that you don't progress. I don't want to sound like a conspiracy theorist, but sometimes you wonder, right? Like why are they giving you mathematical questions that you think will prepare you for the test and whatever, but in reality they don't, and why quite often people have trouble with tests and exams. Okay, and when it came to this, yeah, as I said, I had trouble. I was good at remembering the formulaically how to approach problems, equations, and word problems. But in reality, I didn't understand the problems. I didn't understand word problems because right when the test came, I was failing. Right. So I had a teacher in the end of grade 8 and one in grade 9, and they told me both the same thing. Right. You need to be able to solve non-routine problems. Right. You need to frame your mind in a systems type of thinking way, a systems thinker, if that makes sense. Okay. And what they told me, another thing is that you want to be able to solve problem solving questions with rigor, not just rigor, but with a step by step approach, right? And this was at grade 8. I had a fantastic teacher, right? And he taught me this, right? So he said you have to have a problem solving method. Okay, I sort of went through that. I had trouble finding that method. Okay, I had trouble finding that method. It was already too late. Grade 8, I was already a disaster. I go into grade 9, still somewhat a disaster. Getting a bit better. I'm starting to realize that I need a technique that can help me, and it has to be a technique that's suited for you. Maybe my technique's not suited for you, or maybe it is. Right? Maybe you find value in it. Okay, but the point is, you need a problem-solving technique. Okay, otherwise you will always struggle with mathematics. Okay? And in grade 9, I was having trouble. Mid grade 9, I asked my teacher, what do I do? I don't know what to do. I did have a teacher that told me that I need a problem-solving method for solving mathematics problems. I sort of went into it, and he says, yes, he's absolutely right, right? And he says, why don't you do what your teacher said? I said I didn't find it. He gave me a somewhat of a semantic map of how to go about mathematical problems. And like there's like a common, I don't want to say a common pattern because you can never, I'm not saying that this is going to solve your problems. Mathematics is very hard, but it will give you deeper intuition and strengthen your sixth sense and become logically strong. Okay. So step one is you want to be able to visualize what you're dealing with. Visualize can mean either if it's a geometric or graphical problem, you graph it, you make a mathematical model, you simulate it, and you're able to interpret the behavior. Because if you see the behavior, then you understand it, the problem deeply. Okay. And or if it's just an abstract equation, you just try to translate that equation to words. Because if you explain it in words, then you understand it, right? You have to be able to communicate it. Okay. So step one is you want to visualize the problem. Step two is you want to model it. Modeling means you want to be able to come up with a semantic map of the things that you know and don't know in the problem, regardless of what the problem is. Okay, so that's step two. Step three is you want to be able to execute. So from visualize to model, you want to translate that, whether it's a a geometric visualization, or you translate it into words, right? You want to be able to mathematically come up with quantities and variables from step one, because if you're able to translate step one into quantities and variables, you'll have an equation that you can work with. And then it's just a mathematical technique that you need to use, which is somewhat straightforward. I'm not saying it's straightforward. There's mathematical techniques that are very hard, but I hope you understand that with a lot of problems, you need to be able to set up the problem. Okay. And we're in the execution. And the execution phase is just mainly algebraic. Okay. And then from step three, step four, you want to verify. What I mean by verify, you want to prove that your answer makes sense. Don't just take it for face value. You take it for face value, you will fail your math classes. Okay? I can guarantee it. You want to be able, because a lot of times people think, oh, I got the answer. Yeah, I mathematically, I have the right I have the technique. I know the technique. It's more than the technique. You want to make sure that your logic is solid, that it's airtight. Okay? And the only way to do that is to verify. Verify that it makes sense. Make sure that the visualization makes sense with the algebra. And or if it's something like, I don't know, we're going to prove that left hand equals the right hand, that's the easiest type of verification. But my point is you need to verify your answers before submitting it. Okay? All right, so that's the 4-step technique. And it's on my simulation here, as you can see, right? In the video right next to me. All right, so you want to be able to use that. I discovered this technique in grade 10 myself, using some guidance of what my teacher said. And then both teachers. And then from grade 10, fantastic results. Grade 11, fantastic. Grade 12, fantastic. I got into Carleton University's double major in mathematics and physics, and I scored a 3.85 GPA at the university and graduated. Okay, with phenomenal results. It's very hard to graduate that program. It took me 6.5 years. Normally, a program is 4 years for a bachelor's degree, but this was 6.5. Okay, and then from there, I said to myself, I was more curious about helping people, because it's very common for people who to have trouble with math, right? But I didn't want to be just any person. I wanted to bring value to the people that I help, like serious value, right? We're not any coaching / tutoring agency, right? We actually diagnose what your problem is, okay? And that's how STEM Online Academy was formed. Okay. So let's get back to question 5. All right. So question 5, what was it? Trying to remember question 5. Why do students lose marks when their algebra looks correct? Again, looks correct. The algebra looks correct. Okay. They'll lose marks for two reasons. One, because algebraically the method is missing something and they just rush through the problem. They'll do that in the execution phase. Okay. But more likely, two, they're losing marks because the reasoning is somewhat lacking. Because you also need to have your framework, as I said, right? My four-step method is mainly a framework. You have to set up a correct framework, and then you can algebraically execute your problem. Framework's not there, the algebra is not going to follow. So the reason why you're losing marks is because it may look correct, it may look fancy, you may be using the right technique, but your framework to the problem solving is incorrect. Okay? All right. So I really hope that this video helped you guys understand, as I said, the logical layer, as to why uh, AI can't help you in hard calculus proofs. Okay, uh, it's a main. A lot of people think that AI can help you in hard calculus proofs. It partially can, but mainly it can't for the reasons why I mentioned. Okay, for the questions that I brought up, right? You won't be able to think that way. It doesn't have that creativity to be able to articulate in the way that a coach can help you, right? Or an expert or a specialist. All right. So that's it for this video. Before I get going, I want to mention a few things. There's a free PDF below for those of you who are still not understanding my systems technique, for also old comers and newcomers, new subscribers, right? Get the PDF. It's for free. It's going to help you understand what it is, how to use this technique, where it most commonly comes up in calculus problems and physics problems. Right? I'm also a physics specialist as well. But it's going to really help. All right. And another thing too, if you have trouble with problem solving, in general, right? Sometimes it's more than just a technique, right? Sometimes people will say, "Oh, Jason, I used your technique. It's helping to some degree, or it's not helping at all. But I need a more. I'm having trouble with the internal logic of mathematics. So, like, I'm just not able to deductively put things together." You may find, my book, Axioms, my new book. It's my second book, actually. Uh, it's more appropriate for my audience, I think. That one's really hard. But Axioms is helps you understand, one, how to mathematically think. Number two, how understanding the language of mathematics, and number three, um, the techniques, the logical systems and techniques of thinking, when it comes to proving things, how mathematicians do it. Okay. So if you're struggling with the thinking process, you may want to look at Axioms. Will be in the below. And finally, my coaching services are available. Sometimes people need a one-to-one, face-to-face type of approach, because it's not the same when you're looking at a resource or you're trying to learn it by yourself, especially with an AI. It's not the same thing. You need someone that can actually, you know, read how you're feeling, read how you're understanding things in that topic, and then personalize a strategy for you using my expertise. Okay, because that's something, yeah, you can't take away. Well, that will never be replaced. If we're talking about AI, that will never be replaced, in my opinion. So thanks again. I really appreciate for all my subscribers. I really appreciate the support. Uh, you are what makes this channel still breathing. And for new people, I hope you will like and subscribe. Please like and subscribe. It really helps. Um, Again, thank you. And there's always going to be 2 episodes a week, Tuesdays and Sundays. Uh, again, this is Jason Masterakos, founder and president of STEM Online Academy, and I hope to change. I hope to change a lot of people's lives for the better in education. And I'll see you next time. Bye for now.